Hi, and welcome. I'm Fatima Monji, water resources expert at Deltares and partner in the Stars for Water project. This short video introduces RIBASIM, a river basin simulation model developed to support resilient and sustainable water management in complex basins. RIBASIM is a water resources model designed to help manage complex river basins under current and future challenges. It helps us assess water availability, allocation, and management strategies by simulating how systems respond to different interventions. By the end of this session, you'll understand what RIBASIM is and what problems it addresses, how it supports integrated water management, and what type of data and questions it can work with. I'll provide you some examples of how it's been used in real-world settings. So, this video is meant for water professionals, planners, and anyone dealing with river basin modeling or policy. Water resources are under pressure from population growth, urbanization, and climate change. Effective planning requires tools that simulate the impacts of interventions, scenarios, and infrastructure. RIBASIM helps answer critical questions about both water quantity and quality, so how water is allocated, what happens under drought conditions, and how pollution affects rivers, or how a new dam influences the system. It supports the Stars for Water mission to improve the decision-making through adaptive modeling. RIBASIM accounts for both natural and human drivers. On one side of the scale, we have supply limited not only by natural water availability, but also by water quality, droughts, climate change, upstream developments, or the costs of abstraction and transport. While quantity is often top of mind, if the quality is not fit for purpose, supply is under pressure too. On the other side, we have demand, driven by population growth, irrigation water needs, energy production, or stringent environmental requirements. These pressures don't exist in isolation. They are shaped by larger scenario drivers, socioeconomic changes like urbanization and land use change, and climate change impacts, such as shift in rainfall and evaporation. Traditional hydrological models do a good job at simulating physical processes like river discharge or rainfall, but they struggle with these complex human-driven dynamics. That's where the tools like RIBASIM come in. By capturing both supply and demand and linking them through different scenarios, RIBASIM helps us test measures and interventions, essentially showing what it takes to keep the balance in our water basin. Using a RIBASIM model, you can obtain answers to questions like, what's the optimal allocation of water across sectors, giving priorities and boundary conditions? RIBASIM uses linear programming at each time step to solve water allocation problems, honoring the source and demand priorities and network physics constraints. The optimization is coupled to the mass balance physical layer with the objective of minimizing shortfalls between requested demands and supplied allocation. Another question that RIBASIM can answer, for example, is how do land use or climate change affect flows and quality? RIBASIM can ingest scenario-driven inputs for runoff, recharge, demand, or pollutant loads and simulate how allocation priorities, shortages, and water quality trade-offs evolve. Users can also run sensitivity analysis, for example, what happens if rainfall drops X% while irrigation demand rises Y%, to explore the bundles of future scenarios and their impact on the basin balance. Another question that can be answered, for example, is what are the effects of drought or flood events on water supply and demand? Now, RIBASIM acts as the allocator between the hydrology and impacts. It doesn't generate droughts or floods itself, but it propagates their effects through priorities, capacities, and operating rules, allowing users to quantify system-wide consequences. An external drought or flood scenario can be fed into the model with outputs evaluated through chosen performance metrics. Another question is how can policy or infrastructure improve sustainability and resilience? RIBASIM allows users to test structural measures like reservoirs, diversions, or treatment plants, and non-structural measures such as allocation rules, pricing, or environmental flow requirements. By running these kind of scenarios with and without interventions, decision makers can compare trade-offs, identify winners and losers, and design adaptive strategies that balance supply, demand, and quality. RIBASIM is a robust tool already being used around the world in multiple applications and contexts. It has been used for heavily regulated data-rich river basins to barely managed data-sparse basins. This flexibility is one of RIBASIM's strengths. Because every basin faces its own mix of challenges, whether it's scarcity, quality issues, or competing demands, the model can be tailored to capture those local realities. So wherever water managers are facing the challenge of balancing supply and demand, RIBASIM can support better decisions. First example is the Mekong Delta, one of the world's most important rice-producing regions. The key research question here was, what are the irrigation water needs for rice under different seasons? We are dealing with Mua rice, which is a traditional long-duration rice, mainly rain-fed, but you also have to deal with other varieties like winter-spring, summer-autumn, and autumn-winter rice. A second question was, how much rice production can we expect given the upstream fresh water flows, and when we combine that with climate data, crop calendars, and soil conditions? RIBASIM allowed researchers to bring these different pieces of information together, linking upstream discharges with local agricultural needs. This made it possible to estimate how water availability would affect rice yields across the delta. Here we see some results of the Mekong Delta simulations. On the left is the simulated freshwater supply for the years 2014 to 2016. The user demands are the dots, and the lines are the freshwater links to the user demands. Depending on the supply over time, the dots change color and provide the supplied water in values. In RIBASIM, crop production is usually simulated through the advanced irrigation node. That's the function that connects irrigation water supply, crop water requirements, and soil crop parameters to estimate production or yield reductions under water stress. On the right, we compare the simulated rice production from RIBASIM with the observed production data across different provinces to have some validation. What stands out is how closely the model matches reality. The differences are generally within a few percent points. This shows that RIBASIM can reliably capture the link between water availability and agricultural output. These simulations are powerful because they don't just reproduce the past, they also allow us to explore future scenarios, like climate change impacts or upstream developments. That means they can inform both short-term agricultural planning and long-term water strategy under stress conditions. In short, RIBASIM provided a way to connect hydrology with agriculture, giving decision makers insights into both water allocation and food security in a region where millions depend on rice production. Our second use case is the Meuse Basin, which spans several countries in Western Europe. The research question here was, how will low flow conditions change under different future scenarios? We compared two different scenarios, a sustainable first scenario, which emphasizes the careful and efficient use of water resources, and a national first scenario, which prioritizes economic growth and wealth generation. On the left here, you see the model outputs. We look at a location called Meuse. Meuse requires at least 50 cubic meters a second for its discharge. Currently, the river experiences about 34 days a year with that critical low flow, below that 50 cubic meters a second. But under future scenarios, this could increase dramatically to around 62 or even 75 days a year, depending on the pathway. On the right, you can see the basin network represented in RIBASIM. The dark blue lines show the river system. Blue buckets represent reservoirs and control structures, and the orange squares mark demand nodes, such as urban or industrial areas. These are connected by links that route water through the system, allowing us to simulate how hydrology, infrastructure, and water demands interact. This kind of analysis is essential for water managers because low flow conditions affect navigation, they affect energy production, ecosystems, and drinking water supply. By testing future scenarios, RIBASIM helps decision makers understand risks and plan strategies to reduce vulnerability. Finally, let's look ahead to RIBASIM 2025. RIBASIM has a long history of development, and now the next generation is being built as we speak. The new version will be open source. It will be built in a new modern programming language called Julia and designed for much greater flexibility. It will support standardized input and output formats, integrate seamlessly with tools like QGIS. So the goal here is to make RIBASIM not only more powerful, but also more accessible for researchers, consultants, and water managers worldwide. If you'd like to learn more or get involved, you can find more information at ribasim.org. To summarize, RIBASIM is a powerful tool for sustainable water planning. It simulates the water stocks and flows through a river basin and helps us understand and account the balance between supply, demand, and infrastructure. It supports decision-making under both climate and socio-economic scenarios, whether that means planning for droughts, designing infrastructure, or adapting to climate change. And importantly, it's not just for researchers. It's user-friendly, open to collaboration, and already applied worldwide. So the key takeaway is this. Sustainable water management requires bringing together the natural processes and the human needs, also accounting for external drivers and changing boundary conditions. In this context, RIBASIM is a holistic tool that can help water managers make informed and more resilient choices for future. Before I wrap up, just a few last points. If you'd like to see RIBASIM in action, I recommend checking out Esme's webinar on its application in the Rhine Basin. For those who want to dive deeper, more reading material and training resources are available through the Stars for Water Academy. And of course, if you have any questions or comments, we'd love to hear from you. You can reach us through our website. Thank you very much for your attention.